Sure, great. And thanks everyone for coming. I'm very honored to be able to give this presentation on behalf of this wonderful team. This is the Resource Project, the Resource Exploration and Science of Our Cosmic Environment. We are one of the teams that's supported by CERVI. So I just wanted to give an update on some of the great activities that are going on from all these partner institutions covering government, academia, nonprofits, industry, international, and domestic. So just to lay the groundwork for the foundation for what this team is doing, we're looking at ISRU, In-Situ Resource Utilization. And we know that near the sites of robotic or human exploration, we can enable sustainable and affordable missions of the CERVI target bodies. And so key to using space resources is knowing their location, their quantity, their distribution, and the extractability. So those are some of the topics we're trying to address through this project. And so the operations and the hardware that's associated with each of the ISRU processing steps, so from excavation, transportation, processing, we have to examine, test, and integrate all of these processes to enable effective ISRU. So what I could do is just step through a few of the different activities that are going on now. And we divided these into 3 different tasks to tackle these issues. 1, assess and characterize the resource inventories of the CERVI target bodies, primarily focused on the moon right now, but also some asteroid work. And this is really heavily steeped in the science to understand what is there on the moon with a focus on volatiles and ices. Task 2 is some of the ISRU technology development and testing. So we're actually developing and building hardware, and I want to show you some of that that's going on as well. And task 3 is looking at ConOps, concepts of operations, how we would actually do these missions and next generation tools for doing that, looking at the capabilities that would be needed and human robotic interactions in support of lunar ISRU activities. So I want to give a little advertisement for a talk that's coming up later today. I don't want to steal all of Valentin's thunder, but he's doing some amazing work analyzing LRO NAC images, narrow angle camera, and looking into PSRs, the permanently shadowed regions, where we know that there are large amounts of volatiles that are sequestered in these dark, cold areas. And so when you get these images, it's permanently shadowed, so you don't have sunlight in there. But through very clever processing techniques, Valentin and his team have been able to pull out information from these PSRs, and you can actually see features. And so this is very exciting for both science and peering into these PSRs for the first time, and also for exploration. So here's an example, if we've got a traverse plan, whether it's robotic or human, it really helps to be able to figure out where to enter that PSR, where to exit, where to actually draw your traverse, where can you go, where are there hazards, et cetera, et cetera. So Valentin is giving a talk later today, so I encourage you all to go see that. I think it's at 3:35 p.m. Mountain Time, and it's on the agenda. So he'll tell you much, much more about this exciting work. Some other work that's going on to characterize these lunar polar volatile deposits. This is being led by one of our postdocs, Ariel Deutsch. And she has been looking at the control of surface temperature and the correlation with surface ruggedness at the lunar poles. And this was interesting because we didn't actually expect to be much of a correlation. The poles are very cold in these PSRs. But what we're finding is that there is a relationship. Looking at these ice stability zones where you're cold enough that you're sequestering ice over geologic timescales. And on average, the ice stability zones are smoother than the non-ice stability zones. So there's some softening of topography that's happening, which seems to be correlated with temperature. And this may be consistent with the presence of subsurface ice. And we see this on Earth. We know this happens on Earth and even on Mars, but the temperatures are much higher. So it's a real mystery of how the physical process could actually work in this case. So there's a paper out on this in the Planetary Science Journal looking at the data itself. And there's more work going on to try and understand the underlying physics behind this interesting correlation. We're also looking at the vast amount of data that exists for the moon and pulling that all together and doing that with the eye towards resource prospecting and exploration. So we've teamed with the USGS because USGS has been doing mineral mapping and resource exploration for about a century or so. So they're pretty good at it. So Josh Coyen is one of our prime folks from USGS who's been doing this and pulling together these data sets and doing correlations so you can build predictive capabilities to understand where the resources are, even in places where you don't have ground truth. So what you do is you combine all of these data sets and delineate different categories for different regions: prospective, favorable, permissive, non-permissive. trying to high grade where you'd like to go to look for these resources. And in the interest of time, I will not go through these charts, but this is the technique that's used terrestrially, and now we're applying it to the moon as well, mineral prospectivity mapping. And so essentially what you do is you take in your data, you weight the data sets appropriately, given what you have. And what you want to get out of that is a predictive map of mineral prospectivity. In our case, we're looking at volatiles, ices. And you want to get into the resource potential. And Clive was talking about this a bit yesterday, looking at the potential resources. And then it's a whole nother step to go the next level and see if you actually have reserves. Some other work that's been going on, looking at some of the hardware testing, some field testing. This is being led by our group at MIT under the leadership of David Newman at MIT and a cadre of very capable graduate students. This was some field testing that was done last fall. This is a Boston Dynamics Spot rover. You may have seen this before, but it's been equipped with multiple external sensors because what we're trying to do is understand how can we characterize the lunar environment using low-cost, lightweight instrumentation. And trying to get depth information as well, so imagery and depth, because what you want to do is sort of build up a point cloud, build up topography data. And we've done a lot of work using LiDAR in the field. A lot of teams have done that. A lot of groups have done that. And LiDAR is great, gives you great data. But it's very mass intensive, it's heavy, it's very power intensive, and the data rates are very high. So there are some new commercial products that are coming online, depth cameras, which are more lightweight, low power, lower data rates. And so we're testing some of those options. And so testing it out in the field. And also the MIT group is doing some zero-G testing, looking at dust interference. So how much dust in your line of sight affects that data that's coming up. So this is Cody Page, one of the MIT grad students. I'm flying one of these flights in a chamber with the cameras and looking at how rover wheels could kick up dust and how that could interfere with your LiDAR and your camera data. And then looking at how that compares with the terrestrial data. So where this is leading to is we're really trying to be responsive to something that our NASA Deputy Administrator has promoted
for 7 minutes.
Okay, multiple venues, and trying to build up a virtual reality capability when we're on the moon. We want to bring everyone together. And there's a talk by Jay Greer that opened up this forum about how we're bringing humanity to the moon. And so we want to have the world be able to come with us. So if we can render the moon when we're there with robots, when we're there with humans, so that everyone can follow along and be immersed in that environment. So we're going to do that for that reason, but also for science and exploration, because we can enable scientists to be on site, quote unquote, in a VR environment to do science, and also for the exploration and mission operations side of things. So the group at MIT is developing this virtual mission control center. So you've got basically your mission control, but you don't have to be co-located physically. You can all be together. There's tabletop renderings of your field, of your sites, whether it's your EVA sites, et cetera, but you need that camera data to be able to get that in. And that's why we're doing the testing of the depth cameras. Another technology development that's happening is with Honeybee Robotics. This is super exciting. It's called the Smart Drill, Sensing, Measurement, Analysis, and Reconnaissance Tool. So what we're doing is we're taking the Trident drill, which Chris Zachney talked about yesterday. Trident is flying on the Prime 1 mission and the Viper mission to the moon. And what we're doing is we're taking the sensors and now integrating them into the drill itself. So for Viper and Prime 1, what we do is you drill down 10 centimeters, you bring that bite up, dump those cuttings on the surface of the moon, and then look at them with the instruments that are mounted on the spacecraft. So now what we're doing is taking those instruments and putting them in the drill. So as you drill down, you get those in situ measurements. And what's being integrated now is the neutron spectrometer and the near infrared spectrometer that are both flying on Viper, a camera system. And then because Honeybee, they're always overachievers, they're also adding a temperature sensor and heater and a dielectric spectroscopy probe. So this is really going to be, I think, the next generation of how we do drilling on planetary bodies, because now we are bringing the instruments to the sample instead of bringing the sample to the instruments. And then just some of the other hardware, and I know my time is almost up. This is some of the technology development that's happening at NASA Johnson Space Center under this project, and essentially looking at the soup to nuts process for how you're going to do ISRU, starting with the extraction, and how do you capture? We're focused on water. How do you clean up that water? Going through the electrolysis process, an oxygen dryer system, and then eventually getting to liquefaction. So all of this hardware is being worked at JSC using components that have existed and then new components, and the team is bringing this together through this project. And I think one of the last things I want to talk about is a focus on educator engagement and increasing representation, within our field, and trying to bring more communities along with us on this super exciting journey that we've been hearing about for the past few days. So this work is being led by our co-Is at Howard University and also at Johns Hopkins at APL. And what they're doing is developing culturally relevant engineering design challenges to broaden the participation of Black and Latinx students into this realm. And so this is important because this way students can empathize with the design challenges. They're identifying with stories of engineers and scientists of color at NASA, so they want to help and get involved. This is great. And we want the students to feel empowered to design solutions that can address community-based social justice issues. So trying to bring this all together. And one of the other activities besides running these workshops is developing professional storyboards for people that are on the team and other folks within our community as well. And developing the storyboard and then videos showing, career progressions and, that you can do this too. So with that, I think I'm over and I will end.